Hello, it's Stat 135, Lecture 29. So last time we were talking about non-parametric tests. Now we're going to be generalizing the t-test, which is a parametric test, to more than two groups. This is called analysis of variance, or ANOVA. It's a parametric normal theory test, also called the F-test. And we're going to be comparing the means of two or more continuous populations. So in particular, we're going to talk about a one-way layout, which is the simplest type of ANOVA. This is an experimental design in which independent measurements are made under each of several treatments. And so what we have is we have I treatment groups, each with J observations. Right now we'll assume for each treatment we have the same number of observations. And for each treatment group we have a row sum, or a treatment sum, and our treatment average, and we also can compute the total average, which is the average of the treatment averages. And our model is that the jth observation of the ith treatment group consists of the overall mean plus some differential effect of the ith treatment, plus some noise, which is modeled as a normal random variable with center 0 and variance sigma squared. And we're going to assume that the sum of the differential effects is 0. So the yij are normal mu plus alpha I with variance sigma squared. Our null hypothesis is that all the differential effects are 0. And the alternative is that not all of the differential effects are 0. So here's a picture where I sort of transposed the axes here. So I have my treatment groups on the horizontal axis. So I have 7 labs and measurements for each lab. And I've drawn the total mean mu and some differential effects. So we're testing the null that the differential effects are 0. So now ANOVA is based on the decomposition of the total variance, SST, or the sum of squares total of your data, the intragroup variance, also called SSW, or sum of squares within, and the intergroup variance, SSB, which is the sum of squares between. And so that I have written down formulas here for each of these groups. And so the sum of squares within is basically looking at the differences of observations with that treatment group's mean. The sum of squares total is looking at the differences between observations and the total experimental mean y bar. And the sum of squares between is looking at differences between the row means and the total mean y bar. So the algebraic proof isn't terribly insightful. You can read it on page 408. What I'm going to stress are some properties of this sum, in particular that SSW and SSB are independent random variables. So now to see this important fact, we use from chapter 9 the facts that when x1, xn are IID normal, that x bar and xj minus x bar are independent random variables. This is theorem A, page 195. And also that the sample variance is essentially a chi-squared with n minus 1 degrees of freedom. This is theorem B, page 197. So now the SSB is a function of y bar I dot, and this is because y bar is in fact a function of yi bar dot, and similarly SSW clearly is a function of yij minus yi dot bar. Now if we think that we're fixing I, then yi dot bar, this is going to be x bar in one above here, and yij minus yi bar dot bar. Again, we fixed I. This is xj minus x bar in one above here. So this so these are independent, and it follows then that SSB and SSW are independent. So let's work out an example here. So I is 3 and j is 3. So I have 3 treatment groups and 3 observations per treatment group. So I have so I have my populations, A, B, and C. I mean my treatment groups. And so I draw j from each. And let's say I get this data that I've written out here on the right. So I can compute SST in a straightforward way and get 30. Now, under the null, these 3 treatment groups are all coming from the same population. So, right, because all the differential effects are 0. So in essence, I'm drawing j times, I'm drawing I times j from a single box. And that then gives me that the SST divided by ij minus 1 is going to be the sample variance, and then by fact 2 that I've written here from chapter 6, ij minus 1 times s, but the sample variance over sigma squared is a chi-squared random variable with ij minus 1 degrees of freedom. So we say that SST has ij minus 1 degrees of freedom, assuming the null. So for SSW, same data. We can compute this, and we see that each row here in the sum that I've sort of circled here is j minus 1 times the variance, the sample variance of A, B, or C groups. So working this out, we get 6, and I can write out the SSW over sigma squared as I times j minus 1 times the pooled sample variance divided by sigma squared. And this is a chi-squared with I times j minus 1 degrees of freedom. So we say that SSW has I times j minus 1 degrees of freedom. Finally, for SSB, again, same data. Notice that SSB actually we're summing from j is 1 to j, but the terms that we're summing have no j in them, so there's a lot of sort of repetition of the terms that we're writing out here. But we can see that we get 24, and we can confirm indeed it's true that SST is SSW plus SSB. 30 is 6 plus 24. And so we've confirmed that fact, and also that SSW and SSB are independent. And we also know this chi-squared subtraction property, that if X is a sum of 2 independent chi-squares with degrees of freedom n plus 1 plus n plus 2, X, let's say X is chi-squared with degrees of freedom n1 plus n2, and x1 has degrees of freedom n1, then x2 will be chi-squared with degrees of freedom n2. So here our n1 is I times j minus 1, our n1 plus n2 is ij minus 1, and our n2 is I minus 1. So we say that SSB has I minus 1 degrees of freedom, assuming the null. I'm assuming the null here because to do this I needed that SST has ij minus 1 degrees of freedom, which is only true assuming the null. So now to put this all together with the F distribution, as defined in chapter 6, U and V are independent chi-squared random variables with A and B degrees of freedom. Then the distribution FAB, so this F distribution has two parameters. It's the ratio of U divided by its degrees of freedom and V divided by its degrees of freedom. So the F test, assuming the null is true, has parameters I minus 1, I times j minus 1, which are the between degrees of freedom and the within degrees of freedom. And again, remember the between degrees of freedom assumes the null. So this only is true when we assume the null. So you can work this out and see that this is SSB over I minus 1 divided by SSW divided by I j minus 1. So for our example, I minus 1 is 2 and I times j minus 1 is 6, and we get our test statistic of 12. So now this distribution is assuming the null. So the p-value that we get something as or more extreme is what I've shaded in green here. And if this is less than 0.05, we reject the null, as in the usual way that this works. You can find the p-value as 1 minus pf 12 to 6 in R, and that turns out to be 0.08. So we would reject the null that all the treatments have the same mean. Okay, have a great weekend, and I'll see you next time.